Hello, everyone. We are waiting a couple of minutes to start. Good afternoon from Spain. I am Gracia Olivenza, the General Secretary of the Association of Ibero-American Geological and Mining Surveys, ASMI. On behalf of the ASMI Secretariat and the Board of Directors, we welcome you to this virtual workshop on mining environmental liabilities. First of all, I would like to thank everyone who has registered for this workshop. So far, there have been a total of 350 registrations. Nearly 100 of them are postgraduate students that come from almost every part of the world. Most are from Europe and Latin America, but we also have participants from Africa and Asia. I thank you all for your interest. We have 5 workshop sessions ahead, and we will cover different aspects related to the management of mining environmental liabilities and the reuse of secondary mineral resources. This workshop is part of the STAR project funded by the European Union, which is focused on developing a process to obtain thermoelectric minerals by reusing tetrahedrite, a mineral found in copper mining waste. Thermoelectric materials are materials that absorb waste heat from industry and convert it into electrical energy. This will be discussed in more detail during one of the sessions. Now, I would like to mention a few logistical aspects of the workshop. The agenda with all the sessions is available on ASMI website. Each day, there will be 1 or 2 presentations by experts from different institutions. You can submit your question in the chat. At the end of each session, the speaker will have time to answer some of the questions, depending on how much time we have. Any unanswered question will be addressed on our website too. At the end of the workshop, those who wish to receive a certificate will need to pass a test. We will share the link to the test on the last day of the workshop and by email. We will also provide a space on our website where you can access to the presentations and recordings of the event. Without further additional things, I leave you with my colleague Virginia Luengo, who will introduce the speakers. Thank you, and I hope you find the workshop interesting.
Good afternoon, I'm Virginia and I work in ASGMI Secretariat. Welcome to this workshop again. Today's presentation will focus on the fundamentals of mining environmental liabilities. Now allow me to introduce Dr. Fredy Guzmán, whose presentation is titled Types of Environmental Liabilities in Mining, Methodology for Conducting an Inventory of Dormant or Abandoned Mines. Dr. Fredy Guzmán Martinez has been working at the Mexican Geological Survey for 18 years, where he develops research in the environmental geochemistry field. Dr. Guzmán obtained his PhD in research, modeling, and analysis of risk in the environmental in 2022 at the Polytechnic University of Madrid, where he obtained the distinction of cum laude. In 2013, he obtained a master's degree in engineering from the Pontificia Universidad Católica de Chile and a bachelor's degree in biology from the Instituto Tecnológico Superior de Zacapoaxtla, Puebla, where he obtained a honorable mention in his degree. Dear Fredy, when you can start.
Okay. Thank you very much. I share my presentation. Can you see my presentation?
Yes.
Yes.
Okay. Thank you very much for the presentation. Thank you, Gracia, for the invitation to this workshop. And thank you, Virginia, for all the logistic issues. The topic I want to talk about today is types of environmental liabilities in mining, methodology for conducting an inventory of abandoned mines. Okay, I'm going to start by looking at what are the mining environmental liabilities. And then I move on to components of the MEL or mining environmental liabilities. Then I'm going to aspects that may be affected by the MEL. And to finish, I'm going to talk to you about the methodology for the MEL inventories in Mexico. Okay.
Fredy, disculpa, pon
Sí.
la presentación como presentación para que la veamos a pantalla completa. En la parte de abajo de tu PowerPoint. Es el cuarto icono que está abajo a la derecha.
Este no se ve.
Bueno, se ve, lo que pasa que vemos las diapositivas a la izquierda. Pero bueno, no te preocupes.
A ver. ¿Cierto? ¿Ahí? ¿O no?
No, pero déjalo, que se ve, no te preocupes.
Si no las voy poniendo por aquí. Así se ve mi cursor y todo. ¿O no? ¿Sí se logra ver?
Se ve.
Vale.
Sí se ve.
Vale, perfecto. Entonces la voy a dejar así. Ok. Okay, let's start. Have you ever talked about the mining environmental liabilities? I don't know. A participant in the audience who would like to comment on what are the mining environmental liabilities? For example, I don't know. One participant, please. I can see the participants, but if someone.
They can't speak because they don't have.
Okay.
Yes, but they can write in the chat, but they can't speak because they don't have.
Okay, very good. Okay, don't worry. Okay, let's move. The mining environmental liabilities, as defined as mining elements such as installations, buildings, infrastructure, areas affected by spills, mining waste deposits, section of disturbed water courses, workshop areas, machinery parks, or mineral parks that being currently in the surrounding of abandoned mines and constitute a potential permanent risk to the health and safety of the population, to biodiversity, and the environment. I'm telling you this because it's often talk that MEL are only mining waste, and that is not correct. MEL is all the component of the mining, all the mining elements, okay? And the MEL, for qualify as a MEL, it must meet three essential requirements. The first one is abandoned mines and all mining elements in this abandoned mine, plus constitute a permanent risk for health, biodiversity, and the environment. You need meet these three characteristics for you qualify as a mining environmental liability. Okay? An abandoned mining site or orphan site is like a definition of MEL. It's a mining operation that it's not operational, not actively management, it's not rehabilitated, and it's causing a significant social and environmental issues. And no one is currently responsible for its remediation or rehabilitation. Okay? Let's turn to components of MEL. And this section, it's very important because the MEL can be studied as a holistic thing, not separately. I mean, if you assess or characterize or study a MEL, you need to study all the components. And the components, it's the mine components, for example, subterranean workings or surface working, such as open pit, the beneficiation plants, the process plants, massive mining waste, for example, tiling or leach tailing or wet rock, low-grade ore dumps, slag dumps. Other components, for example, is non-massive mining and industrial wastes, stockpilings, for example, or landfills, waste solution, laboratory waste, or other components, it's annexed infrastructure. For example, camps, water warehouse, office, water networks, roads, bridges, because these are all the components of MEL, and we must evaluate all the components of a site as a whole, not separately. Okay. The next thing I want to talk about is aspect that may be affected by the mel. And this aspect that may be affected by the mel are three: the human health, the infrastructure, and natural resource. In the human health is the health and human integrity. For example, damage to human health. In the second one is infrastructure, roads, public facilities, other infrastructure, mobile property, real estate. For example, the area of potentially affected building. And finally, natural resources, for example, agriculture and livestock area, forests, water resources, protected natural area, flora and fauna. And these three aspects that may affected by the mel is principally affected by three phenomena or incidents: contamination, physical stability, and safety issues. The risk of mel to human health, infrastructure, and natural resource is defined by three principal factors. The first one are the phenomena or incidents: contamination, physical stability, safety issues, exposure pathway, for example, soil, water, wind, food, and a receptor. In this case, human health, infrastructure, and natural resource. If you have these three components, you have a risk derivative of the mel. Okay. Next, we will review the phenomena or incidents which are contamination, physical stability, and security. Contamination. According to Arranz Gonzalez, in the glossary for mining environmental liabilities, contamination is defined as or understood as the addition of any substance to the environment in quantities sufficiently significant to cause significant or measurable effects on living beings, soil, water, atmosphere, or which are present in amounts that exceed the background levels of those found in a nature. Okay. Some examples of contamination from mining environmental liabilities are water contamination or acid mine drainage. These examples are very important in the evaluation of mining environmental liabilities because the impact is very significant in the risk. Okay. About physical stability, risk, and safety issues, they can be defined as likelihood that environmental conditions may cause harm to the human body or health. They vary in nature and magnitude from site to site. For example, open pit on subway mining. Despite being recognized by the public and receive media coverage, they are not as well researched and addressed as pollution risk. And this is very important because in a lot of cases, we study just the pollution risk, but most of the time we study just the pollution risk. But the physical stability risk and safety issues derived from the mining environmental liability, it's very important. For example, the main risk due to physical stability and safety issues can be in abandoned mining shafts, open pits, soil subsidence, dilapidated structures or equipment, residual waste, and sharp pegs on the ground, biological risks. For example, in abandoned mining shafts, in this graphic, we can see the number of fatalities in South Africa per year of reporting. In 2009, 96 fatalities and all fire and poisonous gases in mining shafts. Okay. In 2012, 30 fatalities and 20 about rockfall and 10 collapsed tunnel. It's a lot of fatalities, and it's necessary we evaluate the risk in the mining shafts if you inventory mining environmental liabilities. We can see in the slide a couple examples of mining environmental liabilities in Mexico, in North Mexico, mining shafts. Other examples, it's in, for example, in San Ignacio, in the municipality of Nacosari in Sonora, or La Plomosa in the municipality of Nacosari in Sonora, northern of Mexico. The next one is the open pits. The open pits, in this case, we can see a number of fatalities per year in South Africa. For example, 2 fatalities in 2011. We can see in the Fig A, for example, evidence of a tension crack on the pit retaining wall of abandoned mine. The number of record cases of drawing in water in abandoned pits, for example, and example of people swimming in bodies of water in abandoned open pits. These types of mining environmental liabilities, open pits, are very attractive for the people for activities like swim or fishing, and its instabilities places can pose risks of the human health. For example, in La Plata, Argentina, exists a lot of open pits, and the Nacional de La Plata University inventoried 95 open pits in the city, and this 95, 41, it's cataloged as high dangerous, 26 dangerous, 50 very dangerous, and 13 without dangerous. This study tell all have 1 or 2 deaths per year in Buenos Aires province. And these open pits have 500 hectares at superfice. Okay. Other types of risk is the soil subsidence. The soil subsidence is a landslide, usually due to ground cavities of mining origin. This phenomenon can damage or even destroy buildings and infrastructure located in the affected area. They are weather dependent. For example, in season, in rainy season or dry season, they are influenced by the shape and size of the ground cavities, and they result from intermittent and sequential collapse and the landslide of on-ground mine shafts. This photo is in Ecuador, in Nambija mining district, and we can see the subsidence of soil, the houses near to the subsidence, and the mining shafts that are artisanal mining, or in some case, illegal activity mining. Other topic important that we need to study when you evaluate mining environmental liabilities is the dilapidated structures, all equipment, residual waste, and sharp wrecks on the ground, biological risk. Why? Because, for example, in dilapidated structures, for example, ore storage facilities or buildings, in this case, abandoned mines hostel, ruins of the dilapidated processing plant. The hazard is unstable structures, unstable walls, and the risk is collapse of the structures, falling walls of roofs due to the weaken on safe elements of the structure. Other feature is the all equipments, all types of the equipment and facilities. For example, we can see here all ball mill, mine winches, and these can instability of the equipment, rusty with shaft edge and corners, and falling on people and animals, body cut and piercing when in contact you. Other feature is residual waste and sharp pegs on the ground. For example, empty chemical containers, broken mobile, and residual wastes that walking and falling hazard, getting poisoned by remnants of chemical empty containers. Finally, other feature is the biological risk. While animals inhabit the different parts of the abandoned mine sites, for example, encounter with rattlesnakes, scorpions, spiders, and bats in caves and mine tunnels. The risk is snake bite, might lead to bleeding, severe allergy reaction, tissue death around the bit, breathing problems, amputation, and envenomation, bats, the spread of rabies and staphylococcus, scorpions, spiders. Okay, let's move to the methodology for the MEL inventories in Mexico. In the Mexican Geological Survey, we development inventories for states. We developed a Hidalgo inventory, Chihuahua inventory, and Sonora inventory of mining environmental liabilities in Mexico. The first thing that we have is review the digital database of Mexican Geological Survey. I mean, the cartography, the geological cartography, because in this type of information, you can find the abandoned mines or their inactive mines and you can construct your database for your field trip work. The other thing, important thing that we made is exhaustive bibliographic revision. You can review theses, books, inventories, and all the mining information about your region or your study area. And you, in this type of documents, you can find the abandoned mines and the characteristics and the locations. And finally, in Mexico, the Ministry of Environment have a database, GIS database. You can find the tailing in Mexico that are cataloged as inactive or as abandoned. Okay, you collect all the information and compile in a database, and then you can develop your field work. In our case, we elaborate database information in a GIS, Geographic Information System, in this case in QGIS, and we use an interface denominated QField. QField is an interface and is available on Android, on iOS. It's an app, and this app is free. And the most important, you download in your mobile phone. You don't need data because you just with your GPS of your device, you can use this app, and you integrate a project with all the information that you need for the field work. For example, the probably mails of your phone in field, the database, regions, municipalities, roads, those roads, localities, hydrology, geology, lithology, mining concessions, and all information that you have in your project. And in field, you can draw our polygons. Okay. And we use in all inventories, we use just a GPS, a data collector, that is your mobile phone with the app, a portable XRF miner analyzer. It's very important because it's more cheaper than you send the samples to the laboratory, for example, Sep or other studies. And you need a Sep, 2 millimeter Sep, a multiparameter portable for measuring instruments, principal pH. Okay, how do this? We use a field sheet. The first one, an important information that you need collect in field is the data and place the key of melt. This is very important because you link this key for your samples or for your analysis, or for your risk evaluation. And this is very important. You don't change in the time. You just conserve a unique key of your mail. The name of the mail, the location, it's important because if you return in other times, for example, for rehabilitation or I don't know, for other characterization, you need this information. Is near to the river X, or it's in the ranch Las Margaritas, for example. I don't know. You need a reference, a coordinate system. You need to establish the municipality, altitude, the topographic chart, the name of topographic chart, scale, accessibility, if roads, those roads, lithology. And this information is very important, and it's the first section of the field sheet. Okay. In this slide, we can see 4 mel in the northern of Mexico, in Sonora. In the second section of the field sheet, you choose if your mel is a metallic or non-metallic substance principle. And if the case, metallic, what's substance? I don't know, lead, copper, antimony, mercury, I don't know. The third part is characteristics of the mining, principal mining, and is abandoned, inactive, active. If it's active, obviously don't know is a mining environmental liability, and you can finish your evaluation. If it's underground, open pit, what kind of mining is, some measures. If you have water in the mine, pH, a mining concession in Mexico, it's in the north, there are a lot of mining concessions, and it's very important information in case of a future recuperation of this, for example, mining waste. In this slide, we can see mining waste sampling from mining environmental liability in Sonora, pH measurement in mine water from the Mel San Miguel in Sonora, pH measurement in open pit water from the Mel La Verde, Sonora, sampling preparation from mining environmental liabilities, La Mina Blanca in Sonora, Moctezuma Municipality. I'm sorry. The other section is if you found plants, you mark what method of benefit method, leaching or flotation, I don't know, the process, and you need put all the information about the benefits of mining. The next one is the mining waste deposits. This is very important in case if you found important concentration with potential to reprocess. If you found mining waste, the contamination index, it's a measurement of the potential contamination from your mining wastes. And for this, you can compare your concentration of the elements in the mining waste versus the baseline or the baseline or the other reference levels in your study area. You need this describe sufficiently the deposits with measurements, because this information maybe it's important if you reprocess the mining waste. You need, for example, the density, you need the area, you need the volume, and it's very important information. In this slide, we can see a tailing dump, for example, in Sonora, other mining wastes. And the next one is if you found dangerous substance in the mining environmental liability facilities, you need choose if you found, if yes or no, and what kind of dangerous substance, and observations. And other apart for the field sheet is the around situation. Around situation, 1 kilometer to around, if exists population, roads, urban areas, agriculture or livestock areas, what type of vegetation, natural protected areas, or others. And you specific the name and the approximate distance. For example, we can see this, the Mel Santo Domingo in Acosari, Sonora, Mexico. And you can see it's just in the river and around the forest. The next part of your field sheet, you need collect the information about the water. If it's rain season or dry season, or the temporality of your streams, the name of the principal streams, the distance, the orders, the first, second, third order, and the use of the water. I don't know if it's used for drinking or whatever. And if it's possible, influenced by the mining wastes around the mine. The other topic in the field sheet is the situation of the soils, the texture, if it's sand or lime, if you collect samples, and you can calculate the contamination index, the color of soil, the potentially toxic element that you found in the soils, and observation. The next important topic in your field sheet is the preliminary risk analysis. And we evaluate the risk by 2 criteria. The first one is the probability. And the second one is the severity. In the probability is 0 if you don't, or 0% of occur an incident or a risk. 1 if it's low, maybe doesn't occur. 2 if it's medium, maybe occur the risk. And 3 high if exists, or 100% exists this risk. And the severity 0 if without consequence, 1 low, 2 medium, 3 high, and 5 catastrophic. With probability and severity, you can evaluate preliminary the risk in your mail. For example, you evaluate the contamination, the stability, and the security. The contamination, you can choose, for example, the contamination for waters, for soils, or for dust generation, the probability and the severity. And the probability with the severity, you can obtain a qualify. This qualify is a product of the severity and probability. Contamination, physical stability, subsidence, for example, or breaking of the dam, security problems, fallout in the mine, accidents, or in others, for example, snakes, bats, or other animals present in your facilities. And you can collect samples in your mining environmental liability facilities. In our case, we collect soil samples, sediment samples, mining waste samples, and we collect 2 water samples if we found water in the facilities of the mill. And you have the samples, kind of samples, and location, altitude, pH of soil, pH of water, pH of mining waste. Okay. When you finish all your assessment of your mining environmental liability, we developed a criteria for ranking our PAM. For example, with the preliminary risk, we evaluate and we assign qualify. I don't know, for example, in this case, if the probability is 3 for the human health and the severity is 3, 9 in qualification, okay? And in this risk 9, it's 5 to 15, it's high, okay? We assign 3. The contamination index for the soil, for example, 10. Okay, 10 or 15, 4. So 3 plus 4. And then pH of the water, I don't know, 2. Okay, very high, 4. This tends to respect the mining facilities to the streams, 50 meters, 500 meters, and you assign a qualify. Distance to the locality, to the populations, for example, population. I'm sorry. Okay, with this information, you can rank in your mining environmental liability. The result of A1, A2, A3, B1, B2, C1, C2, C3, D, and E, that is this information, preliminary risk, contamination index of soils on mining waste, pH of soil, of mining waste, water, distance to streams, distance to localities, I'm sorry. Yeah, with those information, you can rank in your mail, okay? This Zoom can permit you obtain if you mining environmental, it's a level very low, low, medium, high, or very high, okay? This information is very important because, for example, in Sonora, nowadays, we have 234 mining environmental liabilities inventory, okay? 200, it's a lot of mails. We need ranking because not is the same the number 1 and the number 200, okay? We need ranking for prioritize the remediation, for example. Okay. And finally, I show you some data for the inventory of mining environmental liabilities in Hidalgo. We found a lot of 1,000 sites. We visit 1,000 sites. For example, we found 751 mining environment liabilities. We inventoried 700, okay? And the 700s, for example, to risk to the human healthy, hike 582. To the infrastructure, 147. And to natural resources, 187. And it's all. Thank you very much for you assist this workshop. Thank you very much.
Thank you very much, Fredy, for your presentation. There are no questions, therefore we can start the following presentation. We will now continue with the next presentation. Let me introduce Catia Prazeres, who will speak about site characterization and sample collection, field and laboratory test. Catia is a geologist in the Department of Mineral Resources and Geophysics in the Laboratório Nacional de Energia y Geologia in Portugal. She got her master's degree in 2011 in the University of Lisbon on the subject of economic geology. He has been working with LNEG Science 28 in different projects in the subjects of geochemistry, geology, and geographic information system. Catia, you can start when you are ready.
Okay, hi, thank you for the invitation and for the organization of the workshop. Let me share my screen. Can you see it?
No yet.
No? Oh. What about now?
Katia, it's in the below part of the screen. It's a square with an arrow.
Yes, but I have to choose which screen to share.
Yes, you
I
need
think
to have open your presentation.
Yes, it's open. I'm trying to. Maybe. No. No. Don't know what's happening, sorry.
If you don't find a way, you can send us by email and we can share. It's no problem.
Okay, let me just try one more time.
Yes, I think it's okay.
No,
Yes,
it's perfect.
we can
Right?
see it.
Yeah.
Yes.
Sorry. Okay.
But now we are seeing your notes and the next slide. Maybe you can put in full screen.
Is it working now?
We
No?
see next slide. If you don't have any note, it's okay.
No, I don't.
Okay.
I think it's a matter of which screen I'm using. So, okay, I'll just keep this one, okay?
Yes, it's okay. We can see it.
Okay. So I work in the Laboratório Nacional de Energia e Geologia, which is the Portuguese Geological Survey. I would like to start by talk about the role of geological surveys on the subject of abandoned mines. As many other countries, we do not have the attribution to recover abandoned mines, as this is designated to a specific institution. However, we do have, as part of the mission of geological survey, to improve the knowledge on the territory, to build databases, to do the mapping that supports and it's the basis for recovery of mining areas, and to do research projects on the dispersion, reuse of these materials, and preservation of mining heritage. This is what we aim for, a sustainable development of these areas, because they do have different life cycles, different phases in time. So nowadays, legislation exists to prevent the mine abandonment and to hold operators responsible for the waste that is generated in a mining operation. We now know that the mine closure should be a part of the mine plan, but that was not the case in the past. And so we have to deal with problems left from the past when there was no ruling. That process of change toward the culture of social and environmental best practices can often be long. So Fredy has spoken about reconnaissance of mining waste sites. As for categorization and inventory, which is the fundamental step towards the knowledge of the territory, the evaluation of a possible situation of risk, or prioritization of projects of rehabilitation or reuse. Not only the inventories, they allow us to compare situations, even between countries. That is something we do in this group. But now I will be focusing on other type of characterization, meaning procedures necessary to study a particular old mining site. I will try to give an overview of the general methods that can be applied to old mining sites characterization. As I mentioned, states all over the world have passed legislation to try to avoid situations of abandonment. as the ones we know were left from the past. This comes in response to a greater societal, economic, and environmental awareness of abandoned mines, and is based mainly on financial assurance mechanisms. Other colleagues will go further into rehabilitation and remediation issues in the next few days. But I would like to say that European Union has a series of recommendations on mining waste, including its characterization. Of course, we need to make a distinction between waste that is being generated now in operating mines and the legacy one, which is the focus here, the abandoned sites. But within the European Critical Raw Materials Act that came out this year, there is mention also for closed and abandoned mines. The Act requires member states to gather data on these old extractive waste sites to be identified and to be studied for their potential as secondary raw materials. Okay, so mine waste is a somewhat vast concept because waste can have several origins. Mining waste can be defined as a part of the materials that result from the exploration, mining, and processing of substances governed by legislations on mines and quarries. The term mining waste regroups, in reality, different products resulting from the extractive industry. Waste rocks consist of non-mineralized and low-grade mineralized rock removed from around or within the ore body during extraction activities. The cutoff grade that differentiates low-grade waste rock from usable ore is an economic distinction and may vary over time. Processing waste or tailings are the waste solids or slurries that remain after the treatment of minerals by separation processes like crushing, grinding, size sorting, flotation, and other techniques to remove the valuable minerals from the less valuable rock. And more specifically, slags are residues from the smelting metallurgical process. Sorry. There is the theme of mine water as well that I won't be addressing. So when we look at an old mining site, we can have different perspectives. The first approach to mining waste has been mainly environmental, but today we look at these materials from other angles and also as raw materials. So studies can have a variety of objectives. It can be about environmental contamination. Some heavy metals are brought into higher concentrations by disturbance than they were before any process. Think of how decreasing particle size makes for an increase in available surface to react. And the removal and crushing of material allows oxygen, whether in the air or in water, to percolate, and let's accelerate oxidation. So this exposure of reactive minerals can generate acidic effluents and runoff waters and acid mine drainage. So this is certainly one point of concern. Our dispersion studies, some elements have great mobility and stream sediments that flow from the mining area can transport them. We may want to look at that. Mineralogy, for example, unstable minerals that form on the surface of acidic environments are studied in their instability or even in their capacity to host heavy metals. Secondary Minerals can immobilize elements in acid mine waters, and so they can act as natural attenuation mechanisms. However, this immobilization can be temporary because many of these efflorescences tend to be soluble and influenced by climate conditions, meaning water availability. So we may want to study that. Risk, of course, geotechnical stability or toxicity, danger of collapse. The size of particles can be such that they are airborne and they can present a risk from inhalation if they carry toxic levels of elements. Or heritage, the use of old mining sites for tourism, as it's being done in many sites. This can be an educational solution to promote knowledge in mineral resources with population. And also from an economic point of view, as a secondary source of raw materials. Mine waste can represent an interesting resource of critical and valuable metals with potential economic use. In many cases, all mining wastes have recoverable grades of metals that were not economic in a certain period, or other potentially interesting metals that were not sought for in the past, but that today may have interest. So either the objective, mine wastes are essentially heterogeneous materials. We have seen how the type of waste can be different because of its origin in the mining process, but other properties make each type of waste heterogeneous, like the grain size, if it's ashes or rock, or the spaces between grains, which make a calculation for density more difficult, or the time of deposition, because different techniques were applied over time according to the available technology, which generates different types of waste. Some mines in Portugal, for example, and many places have been exploited since before the Romans, and the waste piles up since, even though in different forms. Here's an example of some waste mapping where it's possible to map different timings of deposition. Often they can overlap. And sometimes you can find stratification inside a waste pile. So modeling the site we want to study allows us to understand the complex mechanisms involved in mining waste. And this helps us evaluate risk, whether environmental or geotechnical, or optimize our analysis. The first step is to perform geological and mining survey and waste mapping. Cartography at a suitable scale is the basis for further work. Again, to evaluate risk, it's necessary to have good geological control of the area. For example, fractures, degree of alteration, etc., can be used in the analysis. If possible, the different types of waste in each pile of waste should be mapped, meaning the mine history, origin, and type of material present, and or treatment that was applied. I refer again to the variability of waste material. It would be of interest also to refer if it's known, the pathways of or from one place to another, and locations of industrial facilities in the mine site, because those places will likely concentrate the metals. And then the physical and chemical characterization of the waste and sampling. If possible, grade calculations in a further phase. So one way to approach this in a first wider scale is by means of remote sensing airborne surveys. For example, the acquisition of aerial photos and the building of a digital terrain model. One can create accurate 3D models and maps of a given site. And then if the original topography is known, we can calculate the volumes occupied by the waste piles. But even in the case that that information is not available, the surface topography, some estimations can be done to achieve an estimated volume. For example, by running several scenarios with minimum and maximum heights, or interpolating that surface through known reference points. Other indirect methods can be applied at this scale, such as geophysical methods like resistivity, to help understand the internal structure of a tailing deposit based on the resistance materials present in conducting electrical current, or other geophysical methods. Another indirect airborne measurement is hyperspectral airborne data. It's a technique that can be used to map the extension and evolution of weathering products in a mine site. This can be useful also during the recovery phase to evaluate evolution. It allows the mineralogical identification of on inaccessible surfaces and of ephemeral crusts concentrating metals. In fact, it shows the differences in mineralogy throughout the year or in surveys separated in time to put in evidence the effect that climate and water availability have on the formation of such secondary minerals. The minerals coatings change due to hydration from summer to winter, so images can be different. Imaging spectroscopy uses spectral libraries and specific algorithms that have been developed as a reliable technique for mineralogical analysis. A color displays the mineral mapping, showing the preferable locations of the oxidation sequence, in this case for sulfates. This is one of the ways we see old mining sites as natural laboratories and its scientific importance. Rainfall and mass movements inside the waste piles develop micro ridges and micro geomorphological structures. This can also be put in evidence using hyperspectral imaging. Okay, so now on another scale, after the area is mapped in its different typologies, on the field, one may have a first approach chemical characterization using a portable XRF. Portable X-ray fluorescence is a field instrument widely used in geological surveys like soil surveys, mineral exploration, environmental surveys, and in a cost-effective way. It has an X-ray tube that allows to irradiate the analysis spot and then detect its energy response and convert it to concentration. It is a point analysis. This is important to say. It does not act as the laboratory analysis where the whole sample is mixed and analyzed as a whole. The diameter of the analysis spot is in the order of a few millimeters, so attention must be paid to avoid nugget effect and bad representativeness. Another issue to bear in mind with this FRX is that the measurement is the best when it's made on a flat surface, but of course, that's not always the case. There are irregular samples. So the more measurements are taken, the better the confidence in the results. And as many times we are dealing with low concentrations, there's the issue of high detection limits it has for some elements. But anyway, some other indicators can give an idea of the acid generation and metal release potential, such as pH and electrical conductivity. If water is present, it can be measured directly with field instruments. A high electrical conductivity and low pH indicates the tailing oxidation activity. So in cases where acid mine drainage is an issue, there are methods to evaluate the potential of acid mine drainage generation and potential for neutralization with samples taken for laboratory procedures that simulate natural conditions. These tests, more specifically for acid mine drainage, will be covered in the next days. If we are in the stage of monitoring an area, some permanent equipment may be installed on the site, such as piezometers for water or inclinometers to detect instability. And in any case, observation points should always be registered and with coordinates in a pre-filled form, such as for inventory or in another type of annotation. The site and sample registration can be done on a field record, as explained before, in inventory, in a more complex or simpler way, depending on the project. Here's an example for samples registration for the START project, and an example of an Ask Me more complete registration form for site characterization that also contemplates sampling. Okay, sampling. So whereas for soil samples or stream sediments samples or rock sampling, we look to collect a representative sample. A sample that represents an outcrop, that represents a larger area than itself. But in a dumping site, we face a lot of heterogeneity. As mentioned before, we face differences in composition, type of deposition, particle size, etc. So first of all, sampling should be done after classifying the waste type. And this is why sampling strategies will be site-specific. Sampling can be performed on the surface part of the pile or in depth, depending on the type of study. Frequently, it's the superficial fraction that is sampled because it's simpler and more suitable if the objective of the study is to the impact of runoff in material transport. Well, one way to overcome the heterogeneity factor is to collect composite samples in a regular grid as much as possible with random points in between to assure statistical representativeness. A regular grid to provide more robust results covering the whole study site. Although, depending on the objective, there are strategies that privilege the flow directions, for example, or transects, including the waste and surroundings. So other patterns can be applied. This is always site-specific. For a composite sample, one collects several subsamples that will be mixed to form one sample. This will be representative of that immediate area. How many subsamples? This can vary, but between 3 and 10 would be ideal Some authors go until 30 subsamples. It depends. If there is soil or vegetation on the surface, it should be removed. In tailings, an excavation can be done until past the border between the oxidized layer and the underlying non-oxidized. This also allows the separation of the often formed hard pans, which is a layer that marks the barrier to the vertical flow of water. It's a zone where secondary minerals precipitate during sulfide oxidation or carbonate dissolution, and it cements. This rapid precipitation can also form crusts on the surface. If we sample those materials, it should be separate from the underlying sample. So stainless steel instruments should be used to sample to avoid metal contamination from the material, and samples should be stored in plastic bags to be carried to the laboratory. After careful identification and registration of the sampling point. When sampling in depth, equipment different from shovels and augers that can be operated manually by rotation are used, and we have to go to drilling. When it's possible to collect a profile, instruments such as those used for soils can be useful, but that's not always the case in heterogeneous piles containing rocks. However, it's a solution for slurries and fine material. In rock waste, usually it's difficult to apply drilling. If sampling is aiming for efflorescence, sulfate salts, unstable minerals that form on the surface of waste, in those cases, they should be stored in closed containers because of their unstable nature, where differences in water context would have an influence in their composition. These materials in particular are shown to differ according to time of year for the water availability that interferes with their composition. So when monitoring changes over time, it's necessary to sample several times. Samples that come from the field are dried, de-agglomerate when they form chunks, homogenized, and proceed to sieving and analysis. In the case of fine samples, rocks will be crushed and milled or sent to the proper study. Usually samples are split in splitters to obtain equal amounts of sample to follow two different analyses. Typically, the smaller fraction is sent to chemical analysis, the less than 75 micra or so. So if we aim to analyze several fractions to better understand in which grain size metals tend to concentrate, then every sieved fraction will be milled to reduce particle size to the laboratory analysis, but separately after sieving. And it's always a good practice to save an equal sample in archive, because sampling is costly, especially a large sampling campaign, and it's not always possible to go back on the field easily. So in the laboratory, one can access mineralogy, sulfides present, carbonates present, etc., quantification of minerals and its distribution throughout the site. This is an essential step to understand the weathering processes and to know the reactive minerals that result from acid mine drainage and the minerals that can act as barriers. silicates and aluminosilicates tend to have the ability to contain some metals, and thus it's important to identify and quantify it. The mineralogical pattern of the secondary minerals growing on mine waste can vary with time and space and range from mud tailings to rock piles, and vary also with the landforms on the waste piles and dumps. This identification can be made by X-ray diffraction. Although some phases have poor to non-crystalline structures or exist in non-visible fractions, and microscopy techniques should be applied. Scanning electron microscopy, for example, can be used to observe the growth relationships between minerals and help understand stability and mineral behavior, as you see in some images here. Bulk chemistry can provide key elements and element associations, carbon content, etc., can complement and be analyzed together with the mineralogy results. Particle size distribution can be assessed with a laser particle size analyzer, for example, after the samples are dried and homogenized. The grain size distribution can show the heterogeneity and possible grain size stratification inside the pile. Another issue is the presence of voids or spaces between particles. If large pieces of rock are in the pile, the more void spaces and thus density decreases. But with time, some consolidation may happen in depth and particle sorting, transporting small size particles to occupy those empty spaces. Geostatistical modeling can be applied to the results, resulting in maps that can show the distribution of certain elements of interest or groups of elements. For example, we see here the distribution of silver in historic mining wastes. Sequential extraction is another assay that allows to differentiate in which fractions or mineral phases the metals are associated to. In this technique, different extractants are applied to the sample, whose function is to dissolve selectively certain fractions of the sample that contain the elements. Its advantages to be interpreted together with mineralogy. In this case, for example, for sediments, zinc is absorbed onto organic matter and iron oxides preferentially. So at last, a word on reprocessing of mining wastes. It is, as for any commodity production, an evaluation of the economical balance of the mining waste reprocessing using a cost and benefits approach that includes the economic value of metals recovered, the cost of reprocessing, the cost of the remaining materials final disposal, because not all mining waste is viable for recovery. It is true that historic mineral processing techniques were usually less efficient than modern ones, and so historic mine waste may contain significant metal contents or significant contents of commodities that were not of economic interest at the time, which makes the use of secondary raw materials even more interesting from the circularity point of view. This does not mean, however, that content is recoverable. We would have to address mineral processing techniques, which is a whole other issue. But anyway, to have a real possibility to reprocess mining waste and transition waste to a valuable asset, it's necessary to know the wastes, to have information on waste quantities, waste age, or processing characteristics, to perform a carefully planned sampling campaign, access mineralogy and analysis of the material to understand if the grades are significant and if the mineralogy allows the recovery of the metals for any given use. Also, each material may be preferentially accumulated in a different type of waste. In the low-grade waste, the tailings, the slags, and it is site-specific. So we need to know the ore body as well. Only after that, if it's possible, we go to further steps. For start projects, that brings us here, it's the evaluation of tetrahedrite from waste to thermoelectric devices. Some other projects have produced practical results. For example, Bromine produced maps with the anthropogenic sources of mineral resources in Europe. Of course, it's a database at continental scale. Country scale surveys are better suited. More recently, the project GUS is making some efforts in the sense of a more comprehensive database on mining waste, and other projects in a more local scope or in particular aspects are ongoing in Europe. As for reprocessing and reuse, our group in AskMe has a handbook coming out this year. You will be notified, I guess. So as a conclusion and a way to wrap this up, to valorize waste, we need to have data on that waste. So it's important to do fieldwork and analysis, to build databases, and to integrate all knowledge. Thank you for listening. That's all.
Thank you, Katia and Fredy. Is there any question? If is there any question, you can write in the chat, and our speakers can answer you now. All the presentations and recording of the workshop will be shared in our website as soon as we can process the video and we have the presentations. But maybe tomorrow we have this material on the website.
We can wait a few minutes if anyone has any question for the speakers.
I think is there is here a person with the hand up. Vicky, tú puedes darle audio y vídeo a esta persona en el listado. No sé si lo ves, o hazme a mi administradora y si quieres si lo hago yo. Let us open the micro for Fredy Guzmán. Vicky, ¿puedes?
No.
Mira, si pinchas abajo donde pone participantes, te va a salir a la derecha una columna y arriba verás que hay como una manita. Si pinchas ahí.
Fredy Guzmán.
Hello.
Hello, everyone. Can you hear me now?
Yes, we can hear you.
Okay, thank you. So thank you because this workshop is so very important. And I have one question to the Dr. Fredy, because I didn't catch something he said. So Dr. Fredy, I'd like to know the element to put or to how to fill, or the question is the following: how to fill the field which are in the table on the page 49 in order to rank the mail, because I didn't understand which elements are going to be filled this table exactly on the page 49. Thank you. Can I repeat the question or it's okay?
Okay. Hi, Fredy. Thank you for your question. I share again my. This is the table you mentioned. Can you see? Hello, Fredy?
We can see the screen, Fredy. Yes.
Okay. Okay. Hi, Fredy. This criteria we use for ranking the mining environmental liabilities. I mean, if you evaluate each one of these factors in your field sheet, preliminary risk, contamination indices for soil, water, and mining waste, pH for water, for soil, and for mining waste, streams, this stands for streams, and population, you can assessment the ranking for your particular mining environmental liability. And with this, you can ranking all the mining environmental liabilities in your study area or in your region. That is your question?
Yes.
Okay. This methodology, it's our methodology. We don't publish it yet, but in next year or next year maybe we can publish. But you can use, if you want, you can use. And in the Ask Me page, it's www.asgmi.org. You can find our methodology of Ask Me, and you can download a manual for inventory of mining environmental liabilities.
Okay, thank you. Now it's clear.
Thank you too.
I'm going to share the address for this material in our website in the chat. I can't do it.
It will be useful for us.
I'm going to try to do it. No, it's not possible, but we will share this information by email, for example, because in our website, in the section of the expert group of mining environmental liabilities, you have some of the manuals, methodologic developed by the group The problem is that these documents are in Spanish for the moment. But if you can be able to translate it, I think it's going to be useful for you. Katia, I think there is a question in the chat for you. It's from Lucas Portes. We know him. Can you read it, or do you need me to read
Yes,
it?
I can access it. So they're asking about if the if countries in the European Union incentivize somehow the parties interested in conducting an installation like that, like reprocessing mining wastes. Okay, so I suppose that countries, the public sector, what it can do is to increase the knowledge, but then this has to be a private initiative. Some companies that have active mines producing waste, now they look at the waste in a different form now. They look at the waste already in the perspective of knowing it and thinking of reusing it. But with the legacy wastes, it's different because it belongs to no one. So I think the public sector, what it can do is to call the attention to it, developed projects such as the ones we are talking about here, such as START, and then companies have to be interested in doing that. I think that would be my answer.
Thank you, Katia.
We have our, sorry, Gracia, our emails are also available if someone wants to ask something.
So if anyone have any other question, we can end the session for today. We will see tomorrow with a new one, and I hope to see you, everybody, here tomorrow. Thank you very much, Katia and Fredy, and all to the attendees.
Thank you. See you tomorrow.
Thank you very much. See you.
Thank you for all.